So far in line integrals, we've been integrating a function over a curve. Now that curve has either been written sort of as a scalar or with vectors. But now we want to discuss integrating that function over a surface. All right, so how does that work? When we have and these are called surface integrals, by the way. So surface integral is when you have a scalar function, f of x, y, and you can integrate it over a surface S defined by z equals z of x, y. We defined surfaces that way a couple chapters ago. All right, then the double integral over the surface S for that function ds. Okay, so ds, what is that standing for? Right, dA was area. ds is a piece of the surface area. Now, how does that really work? Well, that's what this component is right here. That's the surface area piece, right? What you're doing, if this looks familiar to you, this is the arc length formula. So you're taking your arc length and you're pulling it through an area. So this is arc length. It should look familiar. We've seen arc length looking similar to that back in the day. And you're pulling it through an area, a 2D area. Area is denoted by the A right there. All right, so R is the projection. So this R, right, that region of integration, right, is the projection of your surface area onto the XY plane in this particular instance. Now notice another thing before I go any further. This is the region, this is the surface. Before I go any further, this was all defined for X and Y, but you could also modify the formulas for surfaces that are defined with x equals x of yz or y equals some function y of yz. So we can write it all of those ways as well. The formula is only written with the x and y in mind, but you are expected to be able to modify it as needed. All right, so let's look at an example. We are going to find the surface integral over this function for that surface, right? That surface area piece, where S is the surface of the paraboloid z equals 2x squared plus 2y squared, for 0 is less than or equal to z, which is less than or equal to 8. All right, first we need to look at what this paraboloid looks like. So I graphed it in Maple. There it is. I used a plot 3D. So it's z equals 2x squared plus 2y squared. And of course, because I'm using plot 3D, it assumes z equals, so I don't write z equals. And then I also wanted z equals 0 for that same piece. And you could see the shadow that it's casting, right? That surface is casting a shadow onto the xy plane that we need to think about. And I actually graphed the function as well because that's the color of this object. So you can see down here it's very red, right? And then as we move away from the origin, it's going through the different shades of the rainbow. That's because that was the color. So that way you can see what that integrand is. All right, now I need to draw that on my paper. So it's right here. That's the paraboloid. All right, now it's hitting at 8, right? Because it says 0 is less than or equal to z, which is less than or equal to 8. So we're starting down here at 0, we're going up to 8. Now this surface, S, right, this is our surface, which is z equals 2x squared plus 2y squared. Right, there's that object. And it's casting its shadow down onto the xy plane, and that will be our region, R. Right, so let me kind of draw this down here. Okay, so that's R. So now, right, if this is the surface, S, that I'm drawing, let's draw R as well. And it's obviously a circle. Now the question is, circle of radius what? So let's think about this. this is x squared plus y squared is r squared in polar coordinates. And yes, we are solely switching to polar coordinates in this. So this is 2r squared. So if we think about the top, right, where does the intersection, right? Z equals 8 is 2r squared. So r squared is 4, so r equals 2. So our region is a circle of radius 2. And since it's a circular region, that's why we're going to switch to polar in a second, right? So we think about a spoke coming out. R is going to go from 0 to 2, and theta, because we're doing the whole surface, is going to be 0 to 2 pi. All right, now what about this piece of this formula? I'm going to figure this out first before I go trying to substitute in things, because that will just be crazy. So let's find square root of zx squared plus zy squared plus 1. You don't strictly have to do this first, but it just makes sense because that's going to be tricky. Okay, so this would be equal to the square root of z sub x. So z is right here. Here's our z function, right here. So z with respect to x, the derivative of this with respect to x would be 4x. So I'm going to take 4x, that's z sub x, and I want to square it, plus 4y, and square it, plus 1. Okay, so 4 squared is 16. So this is the square root of 16x squared plus 16y squared plus 1. And knowing that I'm heading for polar coordinates because this is a circle, I'm going to be wise about this and make it 16r squared plus 1, right? Because we can factor out the 16, it leaves you x squared plus y squared, which is r squared. All right, now let's do the integral. All right, so the integral over the surface of e to the x squared plus y squared ds is equal to the double integral over the region now of f of xy. Okay, so we better fix that real quick. We can't use x squared plus y squared if we're going to go to polar, which we are. So this is, of course, r squared, right? This is r squared right here. So we're going to make this e to the r squared, and then square root of 16 r squared plus 1. And then we're going to multiply that by r, dr, d theta. R is going from 0 to 2. Theta is going from 0 to 2 pi. Now we notice that theta is nowhere in here. It's not in the integrand. It's not in the limits of integration. So that means that we can pull 2 pi out and say, hey, this is the integral from 0 to 2. I'm going to bring the r to the front. So r e to the r squared times the square root of 16r squared plus 1 dr. And we are going to make a computer do that. We are not going to do that by hand. No, no, no. And I wanted to show you this because it works out to be a very strange function. It has this IRFE function, which you could go look up in the Maple Help menu for what that means, and it's kind of messy and ugly. And that's when we put in the numeric answer. And we say, please give that to me numerically, thank you. And it gives us to us as 1178, right? 1178.18, right? Now, if you're wondering, what have you found? Well, it depends. But if the function, which was e to the x squared plus y squared, was density, then we actually just found mass. So for example, if it was, the density was, for example, grams per centimeters cubed, right, that's density. And if x, y, and z were in centimeters, right, we would find grams right here. Units were not given, but right, x, y, z in centimeters. Would make them go away, and then you'd have grams as your answer, or the unit for your answer, I should say. Which leads me to the top of the next page, because I just want to review what we've seen so far. If you take the double integral of a region, of 1 over a region, dA, that represents area, right? The area of the region, right, if you will. If you find the double integral of the height for that region, or the triple integral of 1 dV, that represents volume. Technically, it's of solid D, right, because D is right there. All right, and then we learned that if we took the triple integral of density over volume, that represented mass. Of the solid D. All right, so when we do surface integrals, what are we finding? Well, the surface integral of 1 represents the surface area, right? The area of the surface, not the area of the region, right? The area of the surface S. And then if you take the double integral, the surface integral of the density, then that would represent the mass of the surface S. So there's a quick recap of the basic types of double and triple integrals we've learned so far, and then the new ones, the new surface integrals, and what they find.